Okay.
And the recording is
Okay.
starting.
Okay. So I'll continue. I just need to move. Okay. So thanks very much, Isabel David, for the invitation. Randomization is a favorite topic of mine, and it's always a pleasure to meet people from different disciplines as well and to discuss my subject with them and to learn from their subject. So here is a quote from R.A. Fisher, which I'm going to have difficulty seeing because the various things are in the way. Let me read it. The very high odds sometimes claimed for experimental results should usually be discounted, for inaccurate methods of estimating error have far more influence than has the particular standard of significance chosen. I've recently got involved in another debate, which is about reproducibility in general. It's sometimes said that we have a reproducibility crisis, and sometimes p-values, significance tests are blamed. In my opinion, incorrect calculation of standard errors is a much more likely culprit, but that's another talk. So this is what my talk will be about. I will list some common criticisms, including quoting a number of people, primarily philosophers of science. I will then explain why statisticians look at this rather differently and why we're maybe talking at cross purposes. We understand the goal of estimation very differently, and the reason that we do is due to R.A. Fisher. Then I will explain how randomization helps, and then I will give you some open problems. I'm not going to pretend there are no problems. So these are the common criticisms. So, oops. So here is a quote from Alexander Krauss, who wrote an article on this recently. A foundational and strong assumption of RCTs, once the sample is chosen, the achieving good randomization assumption. As long as there are important imbalances, we cannot interpret the different outcomes between the treatment and control groups as simply reflecting the treatment's effectiveness. Researchers thus need to better reduce the degree of known imbalances and thus biased results by better using, for example, larger samples and stratified randomization. Most statisticians would regard this as being simply wrong. Indefinitely many confounders. Even if there's only a small probability that an individual factor is unbalanced, given that there are indefinitely many possible confounding factors, then it would seem to follow that the probability that there is some factor on which the two groups are unbalanced, when, remember, randomly constructed, might for all anyone know be high. This is John Worrell. Most statisticians would not regard this as being wrong, but they would regard it as being completely irrelevant. Balance requires an infinity of randomizations. This is from Borgeson, another philosopher of science. In order to begin to address this problem of confounding factors, just excuse me a minute, the randomization would have to be repeated an indefinite number of times, etc. So basically the argument here is that randomization only works in the long run, and we don't have the long run, life's too short. And then here we have, from an interesting essay by Rocker and Anjum, any difference in outcome between the test group and the control group should be caused by the tested interventions, since all other differences should be homogeneously distributed between the two groups. In fact, statisticians don't believe this. Randomization doesn't achieve this. So the first thing to do is to understand the goal of estimation. And you have to appreciate that the goal must incorporate uncertainty from the very beginning. That's what we have to deal with. The common mistake is to start with a false assumption that error elimination is the necessary goal of experimentation. However, basically what R.A. Fisher understood, and I hope most statisticians do too, is that error is inevitable and must be accepted as such. It's pointless to assume that you can eliminate it. However, what statistical methods do is they calculate not just a point estimate, but an associated measure of uncertainty. Standard error, for example, a confidence interval. In other words, the statistical method accepts that the estimate will be in error, but it tries to tell you how much in error it can be. There's an important difference between the way in which the argument is picked up in the philosophy of science. What the statistical argument is designed to produce is not a perfect point estimate, but a valid probabilistic statement. So that if you want to criticize what the statisticians are doing, criticizing the fact that the estimate is imperfect is regarded as being simply ludicrous by statisticians. We know it's imperfect, and we never said it was. We're making an allowance for the imperfection in the way in which we describe the result, and randomization helps us to do this. And you're not free to imagine anything at all. So let's have a look at Worrell's particular claim about the indefinite confounders. And here I think it would help if people actually tried to get dirty and simulate the problem, to actually simulate what they're claiming has happened. And if you try and simulate this particular problem, you'll soon come across a difficulty. And the difficulty is this: you cannot in your simulation have indefinitely many independent and influential confounders. If you do this, you will find that the variance of the result simply blows up beyond what is possible. You will find, for example, that you have people with blood pressures in thousands of millimeters. Simply impossible. Or that they have forced expiratory volume in 1 second in hundreds of liters. Simply impossible. There is a total variation which has to be respected. And that means that inevitably what happens is the various factors that you add will have to be reduced in importance as you think of more and more of them. Here's an example where I've done a simulation. I've simply simulated a number of different linear predictors from 1 to 7. And the various curves show what would happen to the total variance of the outcome if I didn't, in fact, reduce the importance of the linear predictors as I went along. The variance simply blows up. And I soon reach a stage where the variation that I will see in the outcome is what simply cannot be seen amongst human beings, if we're talking about randomized clinical trial. In fact, this is pointless. If you look at the equation that we would use to predict the outcome, here I have an equation where beta naught is the intercept and Z is the treatment indicator, tau is the treatment estimate I'm trying to estimate, and then I have a number of covariates which I'm allowing to be indefinite. I've got up to xk here, but in fact they could go on and on and on and on and on. But in actual fact, I can simply replace this problem by regarding y, the outcome, as being a function of y star plus the treatment effect, where y star is the linear combination of all of these covariates. Essentially, you can regard y star as being what would happen had the patient been given placebo rather than treatment. And what would happen has been influenced by hundreds and hundreds and hundreds of things. I'll show you a case shortly, in fact, where we're talking about thousands of things which have influenced the outcome. But I don't need to think the thousands of things. I just need to concentrate on the result. What is the net effect of all of the things? And the question then is, can I estimate the net effect of all of the things? And the answer R.A. Fisher came up with was yes. Yes, provided you randomize. Provided you randomize, you can estimate the net effect of all of the things, however many things there are. And Worrell's argument is actually false, because the argument is equivalent to saying the following: I have an indefinite number of terms, the sum is unbounded, but that doesn't necessarily follow. How about the sum s equals 1 plus a half plus a quarter plus an eighth, etc.? That particular sum is bounded by 2. This is well known to any mathematician, and it's rather surprising that a philosopher of science should not see the problem in simultaneously making appeal to an indefinite number of effects and assuming that their particular, any one of them, all of them in fact, could have as much influence as you like. Of course, then in that case, the sum would not be bounded. But is this realistic? No. So how does randomization help? The key is, and this is what Fisher saw, to use the variation within groups to tell you how the groups will vary randomly. The more factors you have, or the more variation that there is, the more plausible it is that patients given the same treatment would vary differently, would vary in their outcome. And so the question is, can the variation that we see within the particular groups, where the treatment is the same, predict to us how much we would see randomly between the groups? And the answer is yes, provided that we use randomization. What randomization means is that the pure random variation between groups may be expected to be equal to the variation within. And this is what the analysis of variance of Fisher is designed to show. And again, I would say, don't talk about randomization unless you know how to carry out an analysis of variance. The estimation and the randomization go together. If you don't understand an analysis of variance, you shouldn't be talking about randomization. It must be accepted that random variation between groups cannot be eliminated. The goal must be to estimate it. And this is what Fisher's combined program of design, randomization, and analysis was designed to achieve. The three things go together. They're intimately linked in the whole program, and you can't talk about one of them without talking about the other. Here's an example, an incomplete blocks trial in asthma. This is a trial I helped design many, many years ago. 7 treatments were being compared in a crossover trial, which is to say each patient acted as their own control. However, the physicians informed the statisticians designing the trial that it was just unreasonable to expect a patient to come back to the clinic 7 times. So we said, okay, how many times can they come back? And they said 5. So we said, okay, what we'll do is we'll run a design in which every patient gets 5 out of the 7 treatments. And we chose the design such that each of the 5 choose 7 possible sequences, or 7 choose 5 possible sequences, was equally represented. In fact, in the end, we used 21 different sequences. Each patient was randomly allocated to one of the 21 sequences, and the patients would receive 5 of the 7 treatments in a particular random order according to the sequence that they were assigned to. So I'm just going to compare 2 of the 7 treatments here, which I shall call ISF24 and MTA6. So I can do this in 2 different ways. I can actually use 71 of the patients who actually received both of these treatments. There were more than 160 patients, but remember, each patient only received 5 of the 7. But I can, in fact, find 71 who received these 2 treatments. But also, I can find 37 patients who were given ISF24, but not MTA6, and 37 who were given MTA6, but not ISF24. So that means that from this very same design, I can in fact perform 2 types of estimation. I can do a within patient comparison using those patients who received both the treatments, and I can use a between patient comparison using those patients who didn't receive the 2 treatments. Here are the results. On the left-hand side, a point estimate, the estimated difference between the 2 in liters of FEV1 of 0.37 for the comparison between patients. And then you have a value of 0.17, which is the within patient comparison. That's based on the 71 patients who got both treatments. And then what I've also included is I've included a meta-analysis of the 2 types of information. And I've also fitted a full linear model, which gives almost the same result, which is 0.18. In fact, what's also included are the confidence intervals. Those bars and whiskers that you see are the measures of uncertainty associated with the 2 things. And you can see that the between patient estimate has a much, much bigger estimate of error associated with it than the within patient one. And this is not surprising. Actually, there are more patients present in the within patient estimate, but also what I've done with the within patient estimate is I've eliminated tens of thousands of covariates. Tens of thousands, you say? How? Well, how many genes are there? Every patient is their own control. So any genetic difference between patients is completely irrelevant once I happen to compare a patient to themselves. Similarly, all life history to date, to the start of the trial, is irrelevant when I compare a patient with themselves. Everything that happened to them is the same up to that moment. From the moment the trial starts, that's not true, but it's still a huge number of things. There are millions and millions and millions of things which are balanced in the within estimate. And there are millions of things which are not balanced in the between estimate. And yet you will see, although this is partly a fortuitous result, the two results. The two confidence intervals include the same full model estimate of 0.18. And this is essentially what randomization does. It says, okay, you can't balance all these things. You can't even see them. You can't even measure them. They're out there. But what we can do is we can use the fact that they will vary within the groups to tell us how much they will vary between the groups. So to say that one of these estimates is more valid than another is to overlook that in actual fact, there is a claim about validity associated with them. And from my point of view, philosophers of science over and over and over again attack the wrong thing. They attack the estimates for not being perfect, which is known, without asking themselves whether the estimates of imperfection which are associated with the estimates are valid or not. So the shocking truth is the following. The validity of conventional analysis of randomized trials does not depend on covariate imbalance. It's valid precisely because they're not perfectly balanced. If they were, the standard analysis would be wrong. If I go to this particular diagram here, the error bars on the left-hand side would be wrong if I had done what there was on the right-hand side. They're allowing for an imbalance. So it's exactly the opposite of what all of these commentators claim. The analysis of clinical trials does not rely on these factors being perfectly balanced. On the contrary, it allows for them being imbalanced, and therefore, in a sense, it relies on them not being balanced, because if they were, the analysis would be wrong. So here's an analogy. To criticize randomization because it does not guarantee balance is like criticizing a bridge builder because thermal expansion means the bridge will stretch, while overlooking the fact that the design explicitly allows for this fact. The statistical analysis has a tolerance built into it. This is what you ought to have to understand if you want to attack randomization. Again, you should know how to carry out an analysis of variance if you want to actually criticize randomization. Okay, so can too much information be harmful? I'm now going to go on to some problems with the argument I've just given you. Here's a game of chance. Two dice are rolled, a red die and a black die. You have to correctly call the odds of a total score of 10, and there are three variants. In game one, you call the odds and the dice are then rolled together. In game two, the red die is rolled first, you're shown the score and then must call the odds. In game three, the red die is rolled first, you're not shown the score and then must call the odds. How should we analyze these three games? So just to help you, here is a table. This is what statisticians grandly call the sample space, showing you the possible outcomes, here the total score of the dice, as a function of the black die score and the red die score. And you will see that there are 36 possible outcomes, which, if the game is played fairly, we'll assume are equally likely if the die is fair. And three of these outcomes, that's where the black die shows a 6 and the red die shows a score, a 4, the black die shows 5 and the red die 5, or the black die shows 4 and the red die shows 6, have a total of 10. So the answer we require for game one is 3 out of 36 equals 1/12. The chance of getting a 10 is 1/12. Now have a look at game two. Here you're given some information. To act rationally, you must condition on the information. And the thing to note is the following. If the red die score is 1, 2, or 3, the probability of a total of 10 is 0. So if, in fact, the red die score is in that particular range, you cannot possibly have a value of 10. If the red die score is 4, 5, or 6, the probability of a total of 10 is 1/6. Now for game number three. Game number three, the die has been rolled, the red die has been rolled, but it's not shown to you. Then in that case, you can argue as follows. There's half a chance that the probability is 0, but there's half a chance that the probability is 1/6, and you end up with 1/12. So in actual fact, what the statisticians would call the marginal argument, that is to say the argument not having seen the extra information, is still valid, even though in theory, if someone were able to see it, they could see the missing information. It would still be reasonable, provided all parties in the game are in ignorance and have not seen the information, to use the marginal or unconditional probability to bet. So the morals, all three games are uncertain and perfect prediction is impossible, but valid probabilistic prediction is possible. You can still make bets even though you can't predict exactly what the score will be. You can't treat game 2 like game 1. You must condition on the information. You can treat game 3 like game 1. And more generally, you can make valid statements about the outcomes of clinical trials provided that you embrace uncertainty. However, you can't ignore an observed prognostic covariate in analyzing a clinical trial just because you have randomized. I don't hold that point of view. And as I'll explain in the next few slides, you can use a technique called analysis of covariance. But you can ignore an unobserved covariate precisely because you did randomize, however many such indefinitely many covariates there are. Here's a simulated example. I'm going to simulate 200 clinical trials. The trials of a bronchodilator against placebo, and I'm going to use simple randomization of 50 patients to each arm. I'm going to balance the numbers per arm. I shall have values at outcome and values at baseline, and I'm going to measure forced expirative volume in 1 second, the very typical outcome measure in asthma trials, in milliliters. And these are the parameter settings for the simulation. The true mean under placebo will be 2,200 milliliters, and under bronchodilators will be 2,500 milliliters. So the treatment effect is the difference between the two, which is 300 milliliters. Remember, I'm the god of this universe in the simulation, so I know what's true. The standard deviation at outcome and baseline is 150 milliliters, but the correlation between the two is not perfect. It's 0.7. These are very standard sort of values one might expect in an asthma clinical trial. What I've done here is I've simulated the point estimates and the confidence intervals. And remember, I'm privileged in this particular case. I happen to know that the true value is 300. And you can see on the left-hand side, those are the 200 results. The values are represented by a diamond, and you can see that they're all over the place. But associated with them are some confidence intervals. And I've highlighted the ones in red that got it wrong. Why do I say got it wrong? Well, they got it wrong in the sense that the confidence interval didn't include the true value, although actually they're 95% confidence intervals. There are no perfect guarantee. But in fact, there are 10 of them here, 10 out of the 200, which is 5%, that don't include the true value, and the remaining ones do. On the right-hand side, I've just blown up the diagram and I've shown you the first 10 so you can see what's going on. Okay, that's fine. And if I don't know that the true value is 300, any one of those, which could be any one clinical trial, is what I would have to accept for the purpose of making statements about the treatment effect. We have to accept that there are no certainties in life. However, supposing somebody reveals to me what the baseline difference between the groups were. Now what I've done is I've organized the particular confidence intervals, the very same confidence intervals I had before. If you have a look at the left-hand side now, the very same confidence intervals, I've organized them according to the baseline difference. I've sorted them by the baseline difference. And now what you'll see is that the red ones, the ones that exclude the true value, tend to cluster either to the left or to the right. This is because once you have been shown that there is an important difference between the two groups, then in that case, the unconditional estimate is no longer completely valid. So what I've done on the right-hand side is I've done what a statistician would do, and that is I've fitted baseline difference in the model. And you will see that what happens immediately is because I've been able to use this information, the confidence intervals have got narrower. I've deliberately kept the Y scale the same. The confidence intervals are now narrower, but also some of them still don't include the true value, but I can no longer recognize where these would occur. Whereas on the left-hand side, I can recognize where they would occur by looking at the baseline difference. I can say, oh, well, the ones where the baseline difference is negative negatively large or positively large are less likely to include the true value, I can't do this anymore. In other words, I have used the information appropriately. But still there are no guarantees. Everything is uncertain, but still I'm able to produce statements of uncertainty that are somehow reasonable. Okay, however, there is a genuine problem here. The problem is that this seems to imply that in making inferences for randomized clinical trials, we must condition on everything we observe. That means all covariates that we observe must be in the model. And the question is, what is the effect on efficiency? And could it mean that more information is worse than less? Well, the answer is yes, in a way, although that's basically due to the standard tools of statistical inference that we use. For example, if we use ordinary least squares, then the Gauss-Markov theorem doesn't apply if we have a stochastic regressor. And basically, by using penalization or equivalently some sort of Bayesian approach, we can probably deal with this up to a point, but otherwise we have to be fairly realistic and say, well, we'll try deal with those covariates we regard as being most important, and it's probably a waste of time trying to do more, but that's another talk. So just to say this, we can do better than ordinary least squares by having random effect models. As I said, the Gauss-Markov theorem does not apply to stochastic regressors, but there are some practical difficulties, and this is an area of ongoing research, and it's an area in which I research myself. And in fact, this morning I was writing a passage for a particular paper to explain what the particular issue is while waiting to come and talk to you all. So it's a genuine area one can have a look at. A pragmatic compromise, which I think many statisticians would go for, is a limited number of prognostic factors. And this, in fact, is what the International Conference on Harmonization E9 guideline suggests. E9 stands for efficacy 9. And this is, in fact, the guideline which governs how clinical trials should be analyzed statistically. So, in fact, it's the statistician's Bible if you work within drug development as you follow the ICH E9 guideline. And all I can say is awareness of the issues seems to be much greater amongst drug regulators and amongst journal editors. As someone who's worked in both pharma and academia, my advice to you is be much more wary of trial results that come from the academic world than those that come from the pharmaceutical world. That's also another talk. So finally, I'm going to leave you with another statement from R.A. Fisher. This is from The Design of Experiments, first published in 1935. Nevertheless, though its logical necessity is easily apprehended, the question of the validity of the estimates of error used in tests of significance was for long ignored and is still often overlooked in practice. Well, unfortunately, more than 85 years later, it's still often looked in practice. And this is a great shame, in my opinion. And whilst I welcome interdisciplinary contact and comment regarding the things we statisticians do, I do think it would be helpful if there was a better understanding of what it is we're trying to do. And that's what I hope this talk has contributed to. Thank you.
Before I start, I should inform everyone that I face some unprecedented problems with my laptop. So if I disappear for some seconds, that means that I will try to be reconnected to the meeting. So my contribution is titled Randomized Controlled Trials, Limitation and Epistemological Aspects. First, we start from a historical fact. In 1948, the first randomized controlled trial published in the British Medical Journal concerning the use of streptomycin in order to treat pulmonary tuberculosis. Then something that is considered today as being the gold standard of evidence-based medicine, randomized controlled trials, to be the gold standard for evidence-based medicine, and being at a top level of hierarchy levels of scientific evidence, just below systematic reviews and meta-analysis. Now we will refer to very briefly to some types of randomized controlled trials. They can be factorial, that means that participants randomly assigned to a group. They may be cluster, that means that pre-specified group is randomly selected for the intervention. Crossover, that means that participants usually receive one intervention and then another time in a randomized sequence. And that has an advantage, that is that participant is both at the test and the control. And parallel group studies, that participants are randomly assigned to a study group and either will or not receive an intervention, and the participant is in the control or the placebo group in that case, and not at the test and control group like crossover studies. And some words for the phases very briefly. According to Vendetti, there is a phase 0 that is very rare, usually used for some drugs used for cancer therapy. Here we only examine the safety and potential of the drug to reach the target area. Here we do not have usually some administration of placebo. They are very rare. They are only used for cancer. The phase 1, which is the most common, we have the participation of a very small number of healthy, mainly participants. It is the first stage we have in which we have the first trial in man, used in man and not in laboratory. Usually we search for the safety doses, and in that phase we do not have usually the administration of placebo. In phase 2 is quite similar than in phase 1. We have a larger number of patients, larger number of participants. We usually have the actual disease or illness in question. And here, efficacy is more important than safety. In phase 3, that is the last stage before market approval, we have a huge number of participants. And here we do not only search for safety, but also for efficacy and effectiveness. And over a short period of time, we have also some kind of control over possible side effects, but only for a short period of time. And phase 4, in some cases, is rare, but is used in medical practice, mostly with some kind of observational studies. We try to focus on the long-term risk of the possible drug administration or the possible treatments. And now we pass to some limitations which are connected with randomized controlled trials. I made the separation of the various categories of limitation. The first category is, let it call, limitations relating with the protocol that we use for randomized controlled trial. Here, one limitation, the first limitation, is that we may have an unrepresentativeness of trial subjects. So, according to that survey conducted by Lee and collaborates, we see that attempts at making cardiovascular randomized controlled trials more inclusive appear to have had limited success. Thus, women and elderly persons remain unrepresented in published trial literature relative to their disease prevalence. Because safety and efficacy can vary as function of sex and age, these enrollment biases undermine efforts to provide evidence. So here we have a case in which we have some kind of excluded, let's say, categories like the researchers are referring to. Another one problem may be the problem of long-term therapy. And so in the research of Rossello in 2015, we can see that little is known about the benefits and risks of the long-term use of cardiovascular drugs. Evidence from randomized clinical trials rarely goes beyond a few years of follow-up, but patients are often given continuous treatment with multiple drugs well into old age. So in this case of cardiovascular drugs, we can see that as the patients start to get older, we do not always had the possibility to monitor what was going on with their long-term therapy. Another one limitation concerning the protocol is the comorbidity. Here is the work of Van Spal. And here we can see that through comparison study, the randomized controlled trials published in a major medical journals do not always clearly report the exclusion criteria. Women, children, the elderly, and those with common medical conditions are frequently excluded from randomized controlled trials, and trials with multiple centers and those involving drug interventions are most likely to have extensive exclusions. Here we have the case of comorbidity as being an criteria for exclusion of certain groups. Now we have some limitations that may be called statistical. And so in many cases in medical practice, the physicians are called to balance or to judge between clinical and statistical significance. We have here research conducted by the Miami Trial Research Group that has been conducted from December 1982 to March 1984. You can see the data, and the outcome is that before randomization, 20% of the patients had normal electrocardiograms, 70% could be classified as having electrocardiographic signs of acute myocardial infarction, and 10% presented with other electrocardiographic abnormalities. Electrocardiographic signs at entry suggested a predominance of anterior wall infractions. The randomized patients were not representative of eligible patients, and the treatment groups were well balanced at entry. So that kind of research ended up to that conclusion, where it seems that in some cases the findings that we could have before randomization may mislead the clinical image and do not provide more precise, let it call, diagnostic criteria according to those who were participating in that study. And some general statistical limitations, mainly from Cartwright and Deaton in the 2018 paper. They have a a paper that extends up to 18 points, if I remember well. These are the first points that I will briefly refer to. The first points concern the bias that may mainly have to do with confounding factors found in randomized control trials and statistical processing. They say that beyond the basis, what we should have is orthogonality of the results, and we should attain, we should expect something like statistically equated results between the populations when we are searching for average treatment effects. And now we move to some limitations that concern the medical practice as such, that is the bias of the easily measurable. And in that kind of bias, we can ask what can be measured, what are the data measured, how do we use those data that we obtain through the trials, and which is the effectiveness of that data that we have analyzed or received. And then we can have the bias in commission research. Desmond and Desmond mainly refer to the case of Britain, in which they adopted a different way of mainly funding scientists. And as we see, we can speak for a turn of science led by scientists to contracts and funding by the government or industry. And how this way of performing experiments by funding and by the government or industry and strict contracts can have relations with some kind of policies, public policies that may affect the role of the scientist and, of course, evidence-based medicine. And now we move to more, let's say, epistemological limitations. It is mainly the work of Nancy Cartwright and Angus Deaton. They have been writing both separately and together for at least 10 and more years. Their research is more centered upon causality, the causal effect. And then, very briefly, I will refer to some of the points that they are referred to. If a randomized controlled trial may work here for a strict protocol, a strict populations, and here is if it has only internal value, internal validity, or if it could be used for another kind of populations, may not have such an external validity. That is really close to what kind of knowledge have the populations that they participate in a study, if they were well informed before they participate. And this is quite close, the problem of knowledge, with the so-called Pearl and Barenboim scheme that says that in order to have a strong evidence, a strong existence of causality, we can not only rely on probabilities. We do not rely only on probabilistic accounts of validation, but we have also to have a great reliance on the evidence found. And here is also a contribution related with Ioannidis, mainly referred to econometrics in that point, in relation, of course, with randomized controlled trials used in medical practice that have to do with the information design and how that information design may have an effect on the credibility of the findings. And then this is also connected with Samson. Cartwright and Deaton refer to Samson, that we always have a contextual account of randomized controlled trials, that they're being performed in a certain context within a certain social scale. And then they end up to some accounts of Mackey's error theory, and how do we can establish causality scheme that also incorporates the parameter of error. But the most important is that Cartwright and Deaton admit that we should have, in many cases, prior knowledge that comes from possibly observational studies when we have to create a protocol for a randomized controlled trial. And in these cases of prior knowledge, beyond the observational studies, policymakers can play an important role during both the design of the protocol, or better, when we are called to interpret the results. And they say that we have to do that we have to always rely on a good argument from the part of the policymakers. They always have to account, to think of both safety, efficacy, and effectiveness before they say something about the treatment or the drug that will go at the market. And that limitations can move from epistemology and then to the issue of mechanistic reasoning, of standalone reasoning, mainly analyzed by Jeremy Howick in 2011. And he starts from the well-known Rossello and Williamson 2007 paper that deals with how we can establish causation. And he starts from both historical and theoretical arguments, the use of antiseptics for the reduction of puerperal fever, how smoking is or not connected with lung cancer, if Helicobacter pylori can cause stomach ulcers, the role that some drugs used in anesthesia, in which we do not have a clear mechanism of their action. Some kind of antiarrhythmic drugs, mainly sildenafil, Viagra, that it has been used for as an antiarrhythmic, but it ended up to used for producing erections. And the other historical example is bloodletting, and this is connected with the humoral theory. Briefly, it can be said that if there is no plausible mechanism from C to E, then any correlation is likely to be spurious. And then Howick poses two problems: that biomedical mechanisms are difficult to identify, and second, that we have difficulty to predict how mechanisms will behave under interventions. So he calls for high quality, valid, and based on complete mechanisms, evidence hierarchies. And he says that knowledge of mechanisms upon which the mechanistic reasoning is based is not incomplete. That is, the mechanisms linking the intervention with the outcome have been identified and their behavior under intervention established. And the second point is that the probabilistic and complex nature of the mechanisms is explicitly considered when inferring from mechanisms to any claims that a particular intervention has a patient-relevant benefit. And then we move to another account of mechanistic reasoning, more centered on the problem of masking, if we can have some kind of masking at the results of randomized controlled trials that is more based on an analysis of knowledge, and I will explain. It is by Michael Wilde in 2021. He starts from Phyllis Hilary and mainly Glennon, and of course Hitchcock, and his considerations revolve around the problem of weight loss. And if weight loss, for example, is connecting with exercising, if exercising is the cause or not of weight loss, or is proper diet, or is something else, maybe a health problem connected with weight loss. And that he says, following earlier, that intervention does not make the relevant overall difference to the health outcome. And also for the second, that causal hypotheses that claim a component effect, and also that are some hypotheses that can claim a net effect. So he adopts the position of Howick that we should adopt a high quality reasoning. But then he strives toward Miriam Salomon about the complexity, chaotic, and multidimensional systems, mainly referring to mammary tumor and radiotherapy. And he ends up that, let me see, do we have something at the, well, I cannot see clearly what's going on.
I sent you a message to tell maybe you should think and conclude in the 5
Yeah,
minutes.
yeah. I'm finishing. Yeah. Can you still see my presentation?
It's kind of frozen, but yeah. I don't know.
Yeah, no, it's good.
Yeah, I'm just concluding.
Okay.
Can you see? Yeah. And then considering those those accounts of wild, I turn to the problem of underdetermination, and mainly through Duhem and Quine thesis, that if we need auxiliary hypothesis in order to substantiate our knowledge through the randomized controlled trials. That starts from the hypothesis that in some cases, either some results may be chaotic or complex, or in some cases that we have some reliance of on prior knowledge. And in order to conclude, I think that Wilde's approach, although is extremely valuable since it poses the problem of analysis of knowledge, and it opens the problem of how the findings of randomized controlled trials may be or not be based upon some kind of first experience rationality, the analysis of Timothy Williamson. I think that it is more preferable to follow the approach of Nancy Cartwright upon examining the social criteria and how these social criteria interweave with the outcomes of the randomized control trials, and if we can have a public policy based on Nad's theory in order to use that kind of instrumental rationality that is connected with Nad's theory. And that underdetermination, the theory of underdetermination, can be work more in cases in which we have conflicting approaches. For example, when we think of which model or theory or method should follow, for example, randomized controlled trials versus observational or placebo-controlled trials. I don't know if you had access to the last slides, but I have finished.